We're continuing with Chapter 11 on infinite sequences and series. We just finished everything related to convergence testing, testing series for convergence or divergence. Now in this video, we're going to go through section 11.8, which is on power series. Before we get started, though, I want to give you some perspective on what we're doing for the remainder of this chapter. Because for me personally, when I was going through calculus, I had a tendency to think about it like, so we're going to learn about power series in this section, and then we're going to learn about other types of series like Taylor and Maclaurin series, right? We're going to learn power series here and then switch to some other topic in the next sections. But that's not really what we're doing. Okay, the goal of these last four sections have really one goal. What we're wanting to do is we're wanting to learn how we can represent a function as an infinite series. So we can say that like the function e to the x is equal to this infinite series. That's just one example. That's it. That's all we're trying to do for the remainder of this chapter, these last four sections. And then, also not just that, but also in the last section, we're going to learn about what do we use this for? What are some applications of representing a function as an infinite series like that? Again, that is it. That's all we're doing. Okay, and now we do this using what's called a power series. Like these Taylor and Maclaurin series, these are power series. Now, in the final section, we're just talking about the Taylor series, and that's just because the Taylor series is just the most general form. The Maclaurin series is centered about zero. The Taylor series is general. You can make a Maclaurin series from a Taylor series by just setting the constant equal to zero. But these are power series. Okay, and so with that in mind, what we're going to do is we're going to start in this section by learning, well, what is a power series? What is that? Okay, now once we've learned what a power series is, in the next section, we're going to think about just the general idea of representing a function as a power series. That concept, that idea, that's what we're going to look at. Then in section 11.10, we're actually going to direct our focus more on the mechanics of doing this, of representing a function as a power series. That's what the Taylor and Maclaurin series are about. And again, the Taylor series is just the most general form of this. Maclaurin series is centered about zero. Taylor series is centered about any number, including zero if you want. And so in the last section, they're just saying applications of Taylor polynomials. Taylor polynomials encompassed Maclaurin polynomials. And why are they calling this a polynomial? We'll see that in a second. But just, okay, what's the applications of these functions represented as series? Okay, so, all right. But what is a power series? That's the first thing we want to talk about. So a power series is a series of the form. It's an infinite series. So you can see going from n is equal to 0 to infinity. And the argument is c sub n times x to the n power, where x is a variable and the c sub n's are constant called the coefficients of the series. So, all right, if we look at this, how does this compare to most of the series we've dealt with so far in this chapter? Well, most of the series we've dealt with don't have like an x in it. They have a variable, but it's in the n. And so with that, each term is a constant. Yeah, it's a function of n, but like you plug in the n is equal to 1, 2, 3, whatever, and you get a constant. And then you're adding, that's the sequence formula, but you're adding the terms of the sequence when it comes to the series. But in this situation, we have a variable, x, that's included in the a sub n. There were a couple of examples where we had a variable like this, but most of the examples we've worked with so far, we didn't have, there was no variable in there. It was just some function of n. So you plugged in the n is equal to whatever, and you got a constant. And that's why the c sub n is a constant. They're calling it a constant. Yeah, it's a function of n, but when in the context of the series, for each term, you plug in the n and you get a constant. But the x here, that has nothing to do with n. In fact, if the x we could factor out the x, but we can't here because you have x to the n. But if you had an x term by itself being like multiplied, you could take the x out of the summation. It has nothing to do with n unless it's like containing an expression with n. Okay? And furthermore, notice that, so we know that n goes from, whatever's defined in the summation. Here's 0 to infinity. But x is not like that. X is x. It's you can input any real number from negative infinity to infinity, right? It's x. It represents it's a continuous variable. Unless, of course, there's a given restriction on x off to the side. But in general, if there's no given restriction, then you can input any x from negative infinity to infinity. It's not like the n, right? It's not even limited to integers like the n, okay? And so now, what else can we notice? Well, so, okay, here's the a sub n, right? If you write out they write out the first four terms here, and so what do you get? What does this result in? So you got this c sub 0, c sub 1, c sub 2, and what do they mean by that? Well, this is a formula for n, right? So depending on the term you're at, you're going to get a different constant, just like we did with regular series, or not regular, but series in the previous sections. This formula for n is going to be, you're going to get a different number for each n. And that's why they're saying c sub 0, c sub 1, c sub 2. But then you have x to the n, so it would be, this is x to the, it starts at 0, x to the 0 is just 1, x to the 1, x to the 2, x to the 3. Okay, so it's a polynomial is what you're getting. It's not really a true polynomial because the only reason is because it goes off to infinity, the order of the polynomial, right? X to the infinity. But like in general, it's got the exact character of a polynomial for sure. Constants, these constant coefficients multiplying x to a integer power that's not less than 1 or not less than 0. That's what a polynomial is. Okay. So now, before we move on, I want to point something out that I think will be really helpful for you. It's something that confused me when I was first going through calculus. And it's that, so, again, as I kind of touched on this at the beginning of the video, but I had a tendency to, I would look at this. Okay, here's the power series. All right. But then like in the next section or upcoming sections, we're going to learn about the Taylor series, the Maclaurin series, and different kinds of series. And that's going to be a different kind of series, right? We'll learn that there's all kinds of different types of series. I was kind of thinking. I don't know, maybe one with like roots in it or something, like you're summing roots and you're doing something with that or whatever. I don't know. But no. For the rest of this chapter, and so in general, for Calculus 2, if you're a Calculus 2 student, in the infinite sequences and series chapter, you learn convergence testing, and then the rest is we're just talking about power series. This is it. We're not going to be looking at different types of series. I'm not a mathematician. I don't even know. I guess there's different types of series than this that have like specific functions, but I don't know. But as far as Calculus 2 goes, as far as this chapter goes, this is it. We're looking at this. This is the power series. This is the only type of series we're dealing with, right? We're going to represent the whole goal of this. The whole goal of these last few sections is to learn how we can represent functions as series. We're going to do that with power series, with this. This is it. Okay, now, also one more thing to mention is, so this name power series, to me, I would hear that name and I would think, oh, so it's a powerful series. It's powerful or something. I don't know. That's what I would tend to think. I don't know the exact history on this, but likely that the name power for power series has to do with the fact that we're summing these power terms here, right? X to the first, x squared, x cubed. It's the sum of these power terms. So just note that as well. Okay. Now, for each fixed x, the series is a series of constants that we can test for convergence or divergence. Right. So what they're saying here is that once you pick an x value, then what happens? Well, once you pick an x value, now you've got just a function of a infinite series that's just a function of n. The a sub n is a function of n. Well, that's exactly what we dealt with in the previous section. The convergence testing half marathon, right? That's one of the series we were given, and we could test it for convergence. Once you pick an x value, but remember, the x value can be anything. The x value is not like the n. The x value is a continuous variable. You can put anything from negative infinity to infinity unless there's a given restriction, like a normal function. Okay, so what you can think about is a power series may converge for some values of x and diverge for other values of x, right? And so, yeah, I mean, you can think about, you could look at any power series. And when I say any power series, again, I mean that's not that many. It's going to be something of this form. Any power series, you're just going to have a different C sub n formula. That's it. That is it. So when I say any power series, that's not like we're talking about some vast array of power series. I mean, yeah, as many C sub n's as you can come up with, but it will always have this form. That's all we're talking about for the remainder of this chapter, okay? So, but you could imagine you could look at you could pick certain values of x and then do a convergence test on it, just like we did, to see if the series converges for that value of x. And so with that in mind, you could think about this series as a function. And why can you do this? Well, because if you determine for which values of x is the series convergent, then you can for those that's the domain of the function. Why is it the domain? Because you can plug in that value of x and get a value, a finite value. That's what the series converging means. And so here's this idea of a infinite series as a function. It's really interesting. Again, the domain of this function is the set of all x for which the series converges. Right? This makes perfect sense. We know that with an infinite series, an infinite series can be convergent. You can have a sum of an infinite number of terms and have a finite value. And we know how to determine if a infinite series is convergent or not. So we could be given a infinite series that has a variable x in it, and it's going to be in this form, and we can, using the convergence testing methods, we can analyze for which values of x, where x could be any real number to start, for which values of x does the series converge. And then we could say that series is a function of x with domain equal to those values where x converges. Notice that f resembles a polynomial. The only difference is that f has infinitely many terms, right? It's like a function is like a polynomial, but with order infinity. Okay, for instance, if we take C sub n is equal to 1 for all n, the power series becomes the geometric series. So you just make here, the vast array of different power series is just what you pick C sub n to be. And here they say C sub n is equal to 1. So what happens? Well, okay, you get this. Well, okay, we know for what values of x this is going to be convergent. When x is, the absolute value of x is between, or just x is between 1 and minus 1, or the absolute value of x is less than 1. It's going to be convergent, 100%. We could actually write what it's going to converge to. It's going to converge to the first term over 1 minus x, or the absolute value of x, right? And it's weird, though. It's really weird when you look at it this way, right? This, if you think about it, we're very, very familiar with this. Because we know if we make x anything between 1 and minus 1, that's going to be, we know that's a geometric series, and we know what it's equal to. The infinite sum, we know exactly what it's equal to. The infinite sum. Right? But this x is weird, but if the idea is if we made x anything between 1 and minus 1, we could write what this is equal to. So we could think about this as a function. Right? But the domain is x has to be between 1 and minus 1, and we could actually put what it's equal to. It'd be the first term over 1 minus the absolute value of x. But then when you write it out this way, it looks weird, right? 1 plus x squared, but that's it though. This is a simple geometric series. when you expand it out, this is what it looks like when you use a variable like this. Okay, it says, in fact, if we put x is equal to 1/2, we get, here's the convergent series. If we put x is equal to 2, it's a divergent series. All right, so now to make this more general, we can actually take so here's you can take the power series formula and you can take the x and put x minus some number a. And if you think about what this means, so just think about it strictly from so again, the f of x has a domain. And that's really powerful because that's telling you where if you, for the domain, you input at x, you get a number, which will be the y value, right? So for the domain, you can plot it. There's a plot of the power series, right? Well, okay, that plot, you can imagine shifting that to the left or the right. How do we know from algebra how to shift a function? Well, if you want to, it's x, you just put x for every x variable, but there's only one x variable here, you put minus a, and this would shift it in the positive direction, positive x direction, a units. You want to go to the left, you put plus a. And so what you're doing there is you're moving the 0 point to the left or the right. That's what you're doing. And so this is the more general form of a power series. This is really, if you want to think about a power series in general, this is what you think about. Because what we had on the previous page, c sub n times x to the n, that was just centered at 0 because a is 0 in that case. Right, so this is a power series. It says in x minus a, or a power series. I'd rather look at it saying it's centered at a, or a power series about a. Notice that in writing out the terms corresponding to n is equal to 0 in equations 1 and 3, we have adopted the convention that x minus a to the 0 is equal to 1, even when x is equal to a. So yeah, the way they define this is, even when there's a special case where if x is equal to a, then every single term becomes 0, but it's defined to where in that case where x is equal to a, for the first term, or for the 0th term, you put c sub 0. You don't say 0 to the 0 power, which is, I think that you can't evaluate that. Yeah, that's undefined. So it's just kind of like a definition. It's a convention for the way you define power series that, for the power series that's centered about a, if you have x is equal to a, then for the first term, you're not going to get 0 to the 0 and it'll be undefined. You just put c sub 0, and then the rest of the terms would go to 0 in that case. Notice also that when x is equal to a, all the terms are 0, at least for n is greater than or equal to 1, and so the power series always converges when x is equal to a. Yeah, that's kind of a trivial case, but you might be saying, well, wait a minute, wouldn't we be adding like c sub 0 an infinite number of times in that case? Well, no. So if you write the series out this way, right, this goes all the way to infinity, these terms. So you plug in x is equal to a, and the infinite number of terms except for the first one are 0. So the infinite series is going to equal c sub 0. So with any power series, and again, if we come back here, just note that even this you can look at as a power series, general power series centered at 0, right? The a is equal to 0 in this case. So any power series that you evaluate x at what it's centered about, whether it be 0 or a, is going to converge. Okay, so remember that. You plug in the value of a power series, that you plug it in x that the power series is centered about, it's going to converge. And what it converges to just depends on the constant term, if there is one. All right, so let's look at this example. For what values of x is this series convergent? Okay, so how do we figure this out? Well, in general, for determining the values of x that a power series is convergent, look, here's the c sub n, right? N factorial in this case. And you always have it's going to be x to the n, every single power series, and that's what we're talking about for the remainder of this chapter. You have x to the n and then some function of n. Here it's n factorial. So for what value? So anytime we're trying to determine the values of x that a power series is convergent, in general, for the most part, we're going to use the ratio or the root test. And that's the case because we're restricted to this, a form like this, right? We're looking at just power series, this x to the n here. So it always, in general, this is going to lend itself to the ratio or the root test. We can't put in like x to the n minus x squared over. No, that would be a power series. This is what we're looking at. So in general, again, if you're finding the values of x for which a power series is convergent, most of the time you're going to use either the ratio or the root test to do this. And so what you do is, what they do, you see here, they do the ratio test, and you assume that x is not equal to 0 because you're dividing by x to the n, right? If x is 0, you can't divide by x. And then what they get is, and then the absolute value is, like we've seen in previous examples, when it comes to the function of n, a lot of times the absolute value is not even going to apply to the function of n, because n is going from 1 to infinity, and that's just the way it works out. But however, when it comes, like, you can just get rid of the absolute value, in other words. However, but this is different though when it comes to the x variable, because the x variable is not going from 1 to infinity. The x can be negative, right? So most of the time you're going to end up with the limit as n goes to infinity of a function of n, but also with some absolute value containing an x expression. Okay, and so when you get to that point, when it comes to like the ratio or the root test, you're going to need to then solve for the values of x that make the resulting limit be less than 1, because that's the criteria for convergence when it comes to the ratio or the root test, right? Well, here, n goes to infinity. There's only one value of x to where this would be convergent. That's x is equal to 0. So it's kind of like a trivial case, right? By the ratio test, the series diverges except for when x is equal to 0. And again, every single power series is going to converge at least one point. So this pretty much means the series is divergent, right? Because again, every power series is going to converge at the center point. All right, for what values of x does this series converge? So they use the ratio test again, and they get, so as n goes to infinity, this goes to 1. And so as n goes to infinity, the absolute value of a sub n plus 1 over a sub n approaches the absolute value of x minus 3, right? We can't just get rid of this absolute value like we do for the n expression, because it's different. This isn't going from 1 to infinity. This can have negative values. So this is the ratio test, though, so we need to solve for what values of x do you get something that's less than 1. Right? This is the limit of a sub n, the absolute value of a sub n plus 1 over a sub n. So when that limit equals something that's less than 1, then the series converges. So this is an absolute value equation, and you get, solving the absolute value equation, we're going to work a bunch of examples. The series converges when x is between 4 and 2, and diverges when x is less than 2 or x is greater than 4. Now, the thing is, though, that the ratio test doesn't give any information like about when so what happens when x is equal to x is exactly equal to 4, or x is exactly equal to 2. Well, then the limit is equal to 1, and the ratio test doesn't tell us anything. So because of that, we need to use another method for if the series converges or diverges at x is equal to 2 or 4. So they plug in x is equal to 4, and they see that that's the harmonic series, which diverges. At x is equal to 2, you get the alternating harmonic series, which converges. So what you get is that the series converges when x is less than 4 and greater than or equal to 2. Interesting. All right. We will see that the main use of a power series is that it provides a way to represent some of the most important functions that arise in mathematics, physics, and chemistry. In particular, the sum of the power series in the next example is called a Bessel function, after the German astronomer Friedrich Bessel. And the function given in exercise 35 is another example of a Bessel function. In fact, these functions first arose when Bessel solved Kepler's equation for describing planetary motion. Since that time, these functions have been applied in many different physical situations, including the temperature distribution in a circular plate and the shape of a vibrating drumhead. Okay, so what they're saying is in physics, engineering, research, right, published papers, every now and then you're going to come across a function that is it's a power series. A function of a variable that you input a variable, have a domain, right? You have a function with a domain for the input variable, like the x. And what you're doing is you're inputting you're saying, okay, I'm going to put in x is equal to 2. That's part of the domain. And it's giving you back an infinite sum value. That's what's going on. And you'll see these kinds of functions every now and then in research and published papers and just engineering and physics, etc. All right, so it says find the domain of the Bessel function. It's of order 0, defined by this. So here's a Bessel function. What's the domain of this? So in other words, for what values of x is this convergent? So they do the ratio test, and we're going to work examples in even complicated examples like this. And so it ends up simplifying for all values of x, no matter what the value of x, the limit is equal to 0, which is less than 1. We're doing the ratio test. So you can input any value of x into this function, and you're going to get a value. That value represents an infinite sum. That's very cool. All right. Recall that the sum of a series is equal to the limit of the sequence of partial sums. So when we define the Bessel function in example 3 as the sum of a series, we mean that for every real number x, so we're thinking about, we can absolutely think about a series as there's the corresponding S sub n sequence. So you have any A sub n, and you can think about it, there's a corresponding S sub n sequence to that A sub n sequence. It corresponds to that A sub n sequence, and that just represents, like, if you put in n is equal to 3 or 4, if you put in n is equal to 3, you're summing that's the sum of the first 3 terms of the sequence. N is equal to 5 is the sum of the first 5 terms. And so if as n goes to infinity, that's the infinite sum of the sequence, if there is one. And that's what you can, even if you don't have an S sub n formula, you can always take the sum, the summation. So here's the infinite sum, right? N is equal to 0 to infinity, but you could just replace the n with an I. That's what they do here. They've replaced the n with an I, and then you go from I is equal, instead of n is equal to 0 to infinity, you go from I is equal to 0 to n. And that's like the S sub n, because you plug in any value of n and you're summing the first n terms of the sequence. That's the S sub n, but the actual infinite sum, though, is that you take the limit as n goes to infinity of this sequence. You find the limit of the sequence. And if that's a finite value, then that's what they're saying here, right? The limit as n goes to infinity of this S sub n of x, that's equal to the function, right? So with that, they as a function of x, they compute the first 4 partial sums. So, okay, this the 0, you're summing just the 0th term. The S sub 1, you're summing the 0th and the first term. S of 2, you're summing the 0th, first, and second term. All right, and so here's some partial sums. These aren't the infinite sums, but and they plot each of these. And what they're saying is that as n gets bigger in this S sub n, you're going to get a plot that's closer and closer and closer to the actual function, the actual infinite sum. Okay? Figure 1 shows the graphs of these partial sums, which are polynomials. They are all approximations to the function, to the actual function. They're approximations, right? But notice the approximations become better and better when more terms are included. Figure 2 shows a more complete graph of the Bessel function. So here, it's the actual function itself. If you added, like, that would be like if you put in n is equal to 500 and you graphed that, you would get something that looks a lot closer to this. But if you did the exact, I think this is the exact plot to where, like, you did the infinite sum. Okay, for the power series that we have looked at so far, the set of values of x for which the series is convergent has always turned out to be an interval, a finite interval for the geometric series in the series in example 2, the infinite interval in example 3, and a collapsed interval. Yeah, so if we come back, we had this geometric series where the interval was -1 to 1, and that's it. This one interval. Same thing in example 2. We had this, it's from 2 to 4, but including 2, not including 4, the single interval, and that was it. And then here we had all real numbers. Or here was just 0. The single number 0. And then here was all real numbers. And it says the following theorem says that this is true in general. You're going to have, when it comes to finding the values of x that result in a convergent power series, you're going to have one of those 3 cases. The series is going to converge at one x value, and that x value is going to be equal to the a, right? So think about what that's saying. That means it's saying that you could not have a power series like that was centered at 3, let's say. You couldn't find that power series converges when x is equal to just 20. And then obviously would also converge when x is equal to 3 as well. You could that wouldn't happen. If it converges at a single point, it'll just be the center point. Otherwise, if it doesn't converge, if it's not the case that it converges at just the center point, then it's going to converge for all x, or it's going to converge over an interval to where there's a positive number r, such that the series it's like kind of like between 1 and -1, right? So that for the geometric series converged over. It didn't converge at a single point. Just the center would be 0. It didn't converge for all real numbers, so it's going to converge over an interval. Then it's going to be that. It must be the case. It can't be the case that you say it converges at x is equal to 3 and that's it. That won't happen. And so if it converges over an interval, they're talking about the radius of convergence, right? Every single power series is going to have if it does converge at least somewhere, it's going to have a radius of convergence. And the radius of convergence for the infinite case would be it's infinity. The radius of convergence for the case where it just converges at the center point, the radius of convergence is 0. But in the other case where you actually have an interval, the radius of convergence is is half of that interval width. So here you go from 1 to -1, that's the interval's 2, so the radius of convergence is 1 here. Here, the radius of convergence is also 1. So furthermore, the radius of convergence is always going to be, it's going to be centered at about the center point as well. So you'll have the center point A, and you're going to have, if there is a convergence, you're either going to just be convergent at the center point, or you're going to be convergent at some radius away from the center point, plus a certain amount, minus a certain amount from the center point, plus infinity, minus infinity maybe. So it's not like you couldn't have here. What they're saying is this was shifted by 3 units to the right. We can't have an interval of convergence of like -5 to -1. Because then that's not centered about the center point, -5 to -1, right? The center point we can see is +3. So the radius of convergence is, again, centered about the center point. And that is the only 3 possibilities for the convergence of a power series. The values of which for x of which the series converges. So the number r in case 3 is called the radius of convergence of the power series. By convention, the radius of convergence is r is equal to 0 in case 1 and r is equal to infinity in case 2. The interval of convergence of a power series is the interval that consists of all values of x for which the series converges. In case 1, the interval consists of just a single point a. In case 2, the interval is minus infinity to infinity. In case 3, that you have, it's just going to be x. So it'll be a plus r, a minus r. But like that's what x, that's the domain of x. You can input into x anything from a plus r to a minus r, right? Because it's always centered about a. What they're saying is you'll never have a power series, even if, let's say it's centered at 3. You're not going to have then the interval of convergence goes from 5 to 2, or 2 to 5. No. Right? If a is equal to 3 in the x minus a term of the power series, you cannot have that the interval of convergence is no, because that's not what's the radius. Then the radius of convergence would be 5, 4, 3, 1.5, but then that means it's centered about like 3.5, and that's not A. So no, you can't have this. Now, but when X is an endpoint of the interval, then anything can happen. The series might converge at one or both endpoints, or it might diverge at both endpoints. So when it comes to the endpoints of the interval, you're going to have to, it's completely random. You could have one of these four cases where here the endpoints don't converge. Here the right endpoint converges, the left doesn't. Here the left converges, the right doesn't. Here both the left and the right converge. Okay, so they give a graphic representation of this here, and they summarize what we just talked about for the different series, the geometric series, example 1, 2, and 3 here. The geometric series, the radius of convergence was 1. It was centered at 0, so the interval was -1 to 1, but they had to just manually check for the endpoint if this was a parentheses or bracket. Here the radius of convergence is 0, so it must converge at the whatever A is. In here, in this case, it's 0. And there's the interval. Here, center point is 3. Radius of convergence is 1. So you just go +1, -1. And then they had to manually check to see if the endpoints were convergent. Here, the radius of convergence was infinity. So you go in plus infinity, minus infinity from the center point. The center point was 0. But you could still have a center point not equal to 0 and have the radius be infinity. And you just go plus infinity from the center point, minus infinity from the center point. All right, in general, the ratio test, or sometimes the root test, should be used to determine the radius of convergence R. Yeah, so it just sets up this way for the way a power series is defined with the x to the n like that. It lends itself to the ratio or the root test, or sometimes the root test. Okay, we use to determine the radius of convergence R, the ratio and the root test always fail when X is an endpoint of the interval convergence. So the endpoints must be checked with some other test. All right, so here's another example. Find the interval of convergence, the radius and interval of convergence. So they do the ratio test, and the limit of the absolute value of a sub n plus 1 over a sub n approaches 3 absolute value of x. As n goes to infinity, approaches 3 absolute value of x. So for what values of x is this 3 absolute value of x less than 1? That's if the absolute value of x is less than 1/3. So that's going to be the radius of convergence, 1/3, centered about x is equal to 0. So -1/3 to 1/3. But they test the endpoints. So x is equal to -1/3. What happens? You get this series, and we can just analyze this just like we did for convergence testing. They see that it's divergent. Now they put in x is equal to +1/3, and now you get this alternating series, and they see that that's convergent. So now they update the interval to put a closed bracket here. Okay, here's another example. Find the radius of convergence and the interval of convergence. So they do the ratio test, and as n goes to infinity, the absolute value of a sub n plus 1 over a sub n approaches this. Solve for what values of x is this less than 1, because it's the ratio test. And they get that the radius is equal to 3, and it's centered at -2, right? You're always, for any power series, you're always going to have x plus a to the n, and then everything else is some function of n. So we see it's centered at -2, so the interval is going to be -2 plus 3 is 1, -2 minus 3 is -5. And then you just have to check if you're going to put it equal to here, you have to check that manually. Right, -5 to 1, they check manually, and they get that it's divergent at both endpoints. Okay, so I think you'll get a much better feel for this after we work a bunch of examples. So let's work some examples, problems. Oh, and actually one last thing I want to mention is, so we're going to see in the example problems, in some of the example problems, that, all right, well, again, the general form of a power series doesn't have to start at 0. It's more about It's more about, a constant term multiplying and x minus a. A lot of times you'll have a is equal to 0 to the n power with these consecutive positive integer powers on the x term. That's the characteristic of a power series. It doesn't have to start at 0. Like, you're not, this constant term out front is not going to have an x in it. You'll have, but the x term will just be strictly x, but then maybe with like x minus something, and then just to the n power, going from like starting at some value and then just consecutively counting up positive integers from there. If it deviates from this at all, then it's not a power series. And this is really important because, again, for the remainder of this chapter, all we're talking about are a power series. The Taylor series, the Maclaurin series, that's all power series, okay? So, okay, but we're going to work some example problems. So some of them might look something like this. Okay, well, wait a minute. It doesn't matter that it starts at 1, but we've got this, we can see this, the c sub n, but this is not, we have 2x minus 1 to the n. That's not the same form. What is this? Well, okay, remember that we did this a lot with geometric series. We were given like a general form of a geometric series, but then there was other problems where we were given a series and it didn't look like the general form of a geometric series. But as long as it's as long as you can at the very least manipulate the a sub n to then put it into the general form, then it's still considered a geometric series. And that's exactly what this is. If you have something like this, like where the leading coefficient on the x is not 1, you can do some algebra and to put it into this form. So, okay, the 2x minus 1 to the n. From that, let's take out a 2. Okay, we haven't changed anything, right? So now we know from the properties of exponents, if we have like ab to the n, that's equal to a to the n, b to the n, right? So we can write this as 2 to the n. And there you go. So now you see we can rewrite this as, so 2 to the n over 5 to the n root n. And there you go. There's your c sub n. And you could actually simplify this further. You could do 2/5 to the n power over root n. So there, oh wait, no, I'm sorry. There's your, there's your c sub n, and then there's this is the classic form, right? If you compare that to this, the center we see, we couldn't see what the center was from this explicitly, but we see the center is 1/2, and that's a, and here is the c sub n. All right, so now let's work some example problems.